Bien, buenos días. Vamos a empezar entonces el segundo día de nuestro workshop. La primera charla del día nos la va a dar Leandro Di Persia. So we're starting the second day of our workshop. The first talk of the day will be delivered by Leandro Di Persia. Now I will say a few words related to Leandro's career, and then he will take the room and he will give his talk. Okay. So Leandro Ezequiel Di Persia received the bioengineering degree from National University of Entre Rios, Argentina in 2003, and the PhD in engineering from National University of Litoral, or UNL for short, Argentina in 2009. During 2004 and 2005, he was a fellow researcher at Doshisha University, Japan. He is an assistant professor in the Department of Informatics at UNL and an independent researcher at CONICET. He was vice director of the Sync Institute, and currently he is director of Artificial Intelligence Engineering undergraduate program at UNL. His research interests include signal processing, pattern recognition, and machine learning applied to audio, speech, biomedical, and bioinformatics data. So thank you very much, Leandro, for being here with us, and you can start your talk now.
Well, hello. Thank you all for coming. And when I was invited here to give my talk, I thought about what can I tell to these people. So I choose to do a little review of several applications I have been working during maybe 15 years in audio speech processing. So this is what I will be presenting today. I will talk about blind source separation, denoising and enhancement, dereverberation, and more recently, this virtual source synthesis. So let's start with this, blind source separation. This was part of my PhD thesis. So it's a little old work, but about 2008, maybe 9 that time. So what is blind source separation? We have, which is called a cocktail party problem. We have several people talking at the same time, and we have some microphones recording all that. And we want to obtain the sources from signals recorded from several microphones, and each microphone get a mixture of several speakers at the same time. And we want to do this in a blind setup. That means that we don't know anything about where the sources are or how are the acoustic properties of the room, etc. So this is a problem that can be seen as a convoluted mixture, because from each source to each microphone we have an impulse response. So this source signal is filtered and arrives to a microphone, so it can get several paths to get the sound to propagate through the microphone, can bound here and get to the microphone. So this is a convoluted mixture that we can put in this way. This is like a matrix vector multiplication, but instead of multiplications, we use convolutions. So this. In this case, I am working with only two sources to simplify the problem. So, and this problem usually is very difficult to solve because these filters are can be very long. Maybe if a room like this maybe has 800 milliseconds of reverberation time, for example, this filter can suppose that we are working at 8 kilohertz of sampling frequency. So maybe this filter has 6,000 taps, for example. So working in time domain with this is very hard. And the usual approach is to switch to time frequency domain using a short time Fourier transform. And this is useful because in frequency domain, the convolution becomes multiplication, so the problem is somewhat simplified. So when I started working in this, the first problem I met was that in that time there was no standard method to evaluate the quality of the resulting separation. And we were interested in speech recognition at that time. So our target application was speech recognition. So I wanted to do speech separation and then use that speech as input to a speech recognizer and try to get good results of that. So my first question was, okay, so how do I know that the system is working well without having to do a speech recognition test for each parameter change I do? So the first work we do was to evaluate the correlation of several distortion measures over the speech signal and the output of a speech recognition system. So this is the first two works we published in signal processing. And the idea was to compare several methodologies, weighted spectral slope distortion, spectral distortion, PSQ, this is perceptual evaluation of speech quality. There are standard measuring methods for audio, but I wanted to see if I could use them to correlate with the result I would obtain in the speech recognition system. And those are the results, and we concluded this is a nonlinear transformed version of PSQ. So the conclusion was that PSQ was the best measure. So from that on, we use always this measure. So going to algorithms themselves, this was the traditional approach. I said this is the mixing problem, and when you did this to take the short-term Fourier transform, we get a problem assuming that the sources and microphone are static, fixed in the room. You get this where the age does not depend on time, so they are fixed, the same. And this, for each frequency, if you fix the frequency, this is a standard independent component analysis problem. The only complication is this is in the complex domain. So the signals are complex, but it's the only complication. So the standard approach at that time was to solve one independent component analysis problem for each frequency band. So I take this frequency and its pair from the other microphone and apply independent component analysis and obtain the separation for this frequency. And then go to the next and so on. So the approach was to get a very complex problem in time domain and solve several small complex, less complex problem in frequency domain. That was the approach. But this has a problem. When you perform independent component analysis, you get random permutations and scalings of the source. So suppose I put colors here to indicate this. So in the first frequency, I get the first source here, but for the second frequency, I get the second source here. So there is an additional problem to try to remove this permutation indeterminacy. So that was the traditional approach. So what we did, this was the mixing system in the standard method, and we did the following simplification. We transformed this mixing model in this mixing model. So we assume that the division of this two impulse response will be stand as a scaling and a delay. So this is a strong hypothesis that is valid if the microphones are near no. So we try to show that this is true by recording impulse responses in a room and showing that they are very similar in shape and they only are a little delayed. So this hypothesis was quite valid. And the important thing is that this allows us to simplify the mixing problem and the separation problem. So this gives us a parametrization of the mixing problem, where if I can determine these parameters alpha, beta, and D1 and D2 for one frequency, I can use them to synthesize separation matrix for all frequencies. That was the idea. So by doing that, we get very good results. Those are traditional alternatives using the method I already explained. And these are our proposals for mixtures with different kind of noises and power of signal to noise ratios, and different versions of our proposal. So we get an important improvement in word recognition rate from the speech recognition system. We get an important improvement in PESQ measure, and we get a very, very, very large improvement in processing time. That is because we only solved one independent component analysis problem instead of many. Yes? And this was published. So, well, then we published another kinds of work derived from this. For example, the important thing here was we do only one independent component analysis for which frequency. So choosing the appropriate frequency to do that was important. So we did this work where we use mutual information to try to identify a good one to use. Well, I don't care. So next, some works on denoising or enhancement. This is a very interesting work with Professor Ruffiner. We did some time ago also. We were trying to enhance speech corrupted by noise. So we took a bio-inspired method using these optical representations derived from an early auditory model. So this is an ear model of how our ear processes frequency information during time. So instead of working with the short time Fourier transform, we work in the auditory transform domain. Say that. So in this domain, we used some dictionary-based method to identify a dictionary to synthesize the auditory spectrums. So what we did was to learn two dictionaries, one coming from speech signals and one coming from noise. So we get dictionaries to represent speech and noise. And we put the dictionary together this way. And when we get a speech which is contaminated with noise, we analyze that speech with this dictionary with the two parts, speech and noise elements. So then if we partition this, we can reconstruct the part which is expanded only by speech atoms and only by speech noise atoms. Then we can get approximation of speech and noise. This is the other part. So we can select this part and get the activation for those atoms and only for speech and reconstruct any speech. And by inverse ear model, get the signal. But this was not so good, so we tried to get better ways to obtain the output. So the first approach was what I described, obtaining the clean speech by eliminating the part corresponding to noise. But in the second approach, what we did is use this to get an estimation of the noise, and then use the noisy speech as estimation of the source and use them in a time frequency linear filter to improve this signal. This is the second approach. And in the third approach, we use it both estimation from the model. So we use the speech estimation and noise estimation for the linear filter and apply it to get the clean speech. So we try to evaluate which of them was the best approach. Again, we use some objective quality measure by PESQ and segmental signal to noise ratio, and compare this with different approaches, other approaches for speech denoising, and get very good results for this application. Those are standard methods for speech enhancement, and we show that our third approach was the best one. And this was published in Digital Signal Processing in 2010. Then the other method for enhancement, this is a work we did also with Professor Ruffiner and a researcher from Costa Rica. In this case, what we used was a long short-term memory model neural network. And this was in the denoising autoencoder model. I don't know if you are familiar with denoising autoencoder. An autoencoder tried to put the same input as the output. So, in the noisy autoencoder, you put a noisy input, put clean output, and try to make the network learn how to denoise that signal. So instead of working with the signal itself, we work with some parametrization, so parametric model using MFCC. This is a coder that this coder can analyze and produce these parameters and then can reconstruct the signal from it. So what we did is, instead of denoising the speech signal, denoise the parameters. So this was tested with Arctic CMU dataset and different noise kinds and different noise power. And well, again, we tested this with different alternatives, and our proposal was to, we used two proposals, really. We tested using as input the speech, the noisy speech signal, get to the network of the signal. And the second alternative we tested was the use of a pre-enhanced speech by using a Wiener filter. So but the problem was that the Wiener filter was too aggressive. So it can make the noise, but it destroys a lot the speech signal itself. So the idea was that use the Wiener filter to enhance, to eliminate the noise, but the autoencoder would then reconstruct the speech that was lost by the too aggressive. And effectively, we get that this approach, hybrid Wiener and LSTM method, was the best alternative. And this was presented in the International World Conference on Biosphere Intelligence in 2018. You can see that through time, we slowly make the change from pure signal processing approaches to incorporate more and more neural networks. And there are some examples. You can see here how this is for pink noise, 10 dB of signal-to-noise ratio. You can see how the Wiener filter is too aggressive. It eliminates. This is for -10 dB signal-to-noise ratio. So Wiener filter can eliminate the noise, but it's too aggressive. It destroys the signal. And this method can reconstruct very good speech from that. I'm going too fast. If there is any question, please stop me and ask. So next we can discuss some dereverberation. This is another problem we have when processing speech, is that even if I am speaking by myself in this room, there is reverberation that will distort the speech, and speech recognition systems or other kind of system will degrade its performance with this reverberation. So we were interested in reducing the reverberation effect. This is an example of how you see a clean speech spectrogram and how you see it when it is recorded in a reverberant room. So what can be seen is like this. Is like I get to wash the spectrogram with my hand and distort it in this direction, something like that. What? That is effect of reverberation, and that can be modeled. So in time domain, we get the clean speech convolved with the impulse response of the room. And if we apply a short time Fourier transform and do some simplifications, maths there, we can get to this model where x is not the short time Fourier transform, but the magnitude of square short time Fourier transform. So we can see the magnitude of the short time Fourier transform squared can be presented as a convolution for each frequency. For each frequency, a convolution along the time of the clean speech magnitude squared spectrogram with the impulse response. So now, how we can address this? We use a convolutive non-negative matrix factorization. So if you can see, this is a product of two matrices for each time tau. This is a product of two matrices that are non-negative because they are square magnitude of powers. So, and this is a convolutive model made of many of those matrix products. So that is precisely a convolutive non-negative matrix factorization model. In this non-negative matrix factorization problem, what we do is to, in standard non-negative, not convolutive, we try to factorize the matrix of non-negative values in the product of two matrices. So this is an extended version of that for convolutive relations. So in order to solve that non-negative matrix factorization model, we propose a cost function based on some Frobenius norm of the difference from the real signal and now synthesize using this model. And also put some constraint in the as regularizers for S and H there, to get better property of those matrices. And well, we can, I will not enter in the details of the algorithm, but we demonstrated that we can optimize this cost function using a method based on convolutive negative matrix factorization. And we evaluated this comparing it to the reverberant signal and other alternatives. And this is our alternative Bayesian, the reverberation, because the negative matrix model is a Bayesian for the posterior probability. And we evaluated this in different reverberation times, and we get very good results for our method. And this was with synthetic speech. We used an artificial room, virtual room, to reverberate the signals, so we can change the reverberation and do a more finer evaluation. But then we tried in real speech recorded in a real room. We also get very good results for our method in these three objective measures that are specially used in this field to evaluate the reverberation results. It is not our work, but other people already determined that those metrics were good for the problem, so we used them. This was a work with Francisco Ibarrola that was a PhD student, and now he is working in Australia, so he was successful. And then we continued working in this. We used the same convolutive model, but now we say, why don't we try to factorize also this S? We want to get a model for the speech, a dictionary that can synthesize clean speech. That was our idea. So we also decompose this S in the product of two matrices. One is a dictionary for synthesizing S, and these are the coefficients needed for the synthesis. So it's a more complex model. And instead of using as the cost function, we use the Frobenius norm. But instead of using the Frobenius norm, we now use beta divergence, which is a parameterized divergence that can, if you change beta, you can have the Frobenius norm for one value of beta, but you can get the Kullback-Leibler divergence by another beta. You can get Itakura-Saito divergence by another beta. So we have a wide variety of options for different kind of beta selection. So we modify the cost function to get the beta divergence and some regularizers over U and H. This is an example. If you have a clean speech signal, we can get different dictionaries if you use LDOS distances. So Frobenius distance, we get this kind of dictionaries. And if you use Kullback-Leibler divergence, you get this kind of dictionaries where high frequency are dotted represented. And with Itakura-Saito divergence, we get even better representation of high frequencies. So which one we use, which beta we use? I don't know. Let's see. So the final algorithm has two stages. This is the first stage and this is the second stage. In the first stage, the objective is to get the dictionary W. And in this part, we assume that there is no reverberation. We put an impulse there fixed. We fix H to this and try to learn W and U to get this part of the signal representation. And then when we get the W dictionary for synthesizing speech, then we let the reverberation be learned and retrain the model. And we get this, that is the estimation of the clean speech with the reverberation removed. So in this process, we realized that the two steps didn't need to have the same beta in the divergence. So we can use one value of beta to get the best possible dictionary and then switch the beta to measure better the reconstruction. So that's the name switching divergence. Switch the divergence. And we did some experiment to show that if we don't use the same beta, we get better results. The minimum here is not in the same beta for both parts. And well, again, we do some tests with simulated room and real room. We got very good results in the measures. So this was published in Transaction on Audio, Speech and Language in 2019. Going too fast. Is there any question up here? Okay. So for the last part of the presentation, I will present this. This is a more recent unpublished investigation. This was the work of It was a work of two undergraduate students under my direction, and they presented their final project last Friday. So it's quite recent. The idea here is the following. So we have seen in the first method that we can use multiple microphones to do things like source separation, or for example, speech localization, direction of arrival. So with several microphones, you can detect from where the speech is coming. So for all those applications, we need several microphones. That requires having hardware, some kind of equipment devoted to that, and you need synchronization between the channels. So it's not so easy. It's not just a simple recording the channels. You need to synchronize them. So our idea was to try to see if we can record only one microphone and synthesize a virtual one that would resemble the results we would have obtained with the real microphone. And to do so, we used a neural network in a special case of neural network, deep neural network called UNet, but one-dimensional. So this is convolutions one dimension to the speech signal. So the problem was that using, suppose, this microphone as input, I want to synthesize what this microphone will sense. So we need to get some properties of that. We want the synthesized speech to be the most similar possible to the real one. But the important thing is that we need the synthesized signal to capture the acoustic properties of the room. So we can use it in methods that exploit the acoustic property of the space, the room, to do blind source separation or direction of arrival. So if we don't preserve the acoustic information of the room, we will not be able to use any method over that data. So we need to check both things. If the speech signal synthesized is good, is similar to the one of the microphone 2, but also if the acoustic property of the room were well preserved in the besides speech. Okay? So why do we want to do that? To reduce hardware requirement. And if we succeed, we can use the output in any microphone array processing approach, the direction of arrival, blind source separation, enhancement, multi-channel enhancement, for instance, using multiple microphones as output. So we use two configuration of speech signal. One was a recording I made many years ago when I was in Japan in a real room. So there was data from the Spanish database recorded in a real room simulator they have in Japan. And but they were too few sentences, especially to train a large neural network. They are too few. So what we did also was to use virtual rooms with the same spatial configuration of the cases we have, the real cases we have. And in this case, we use TNIT dataset. And then we could have a lot more of signals to train the network. In this case, we did a kind of one speaker and leave one speaker and sentence out by cross validation. So for each speaker, we leave one of his sentences out for validation and train with all the other speakers and sentences. We remove the sentence for test also, and do that for all combinations also, to get better estimation of results. As a loss function, we use a combination of mean average error in the time domain, but also we add a second term measuring the discrepancy in the time frequency domain. So we measure both domains to guarantee the quality of the speech synthesis. Well, and we have to do many search of many hyperparameters And we got very interesting results. Here we present for each measure 3 bars. These 3 bars are, in the first case, we measure the PESQ when we compare the synthesized signal with the real signal of microphone 2. So this tells us if the synthesized signal is similar to the one it is supposed to be. Okay? So the second measure is between the synthesized speech and the first channel. So we wanted to see if the first channel was the input. So we need it to be less similar to the first channel. It needs to be similar to the second channel, less similar to the first channel. So we get that. And the third bar is the comparison between channel 1 and channel 2 real. So we need to get a reference of how similar they were to know if we are doing it right. So we can see that we get very good results. For example, in the mean square error, you can see the synthesized signal is more similar to the one it tends to be similar than the other. Well, that was for real recordings, and this was for artificial synthesized recording. We get a lot better results here because we got many more signals to train the neural network, so it is expected to get better results here. Also, we can see that the speech quality was very, very good. We cannot, you hear that speech and you cannot distinguish for real speech. There is no artifacts or audible glitches. So it's perfect. And finally, we used the synthesized speech. So the real channel 1 and the synthesized channel 2 as input for a direction of arrival method. This is to test if the synthesized speech has preserved the spatial properties of the room, the acoustic properties. So we compare here the when we in blue there is the 2 real signals used as input as direction of arrival, and this is the error of the estimation of the under profile. So if you use the real signal, we get the blue line. If you use 1 real and 1 synthesized, we get the red one. And this is the difference between both. So in the real recording case, we get those results for 2 different methods of direction of arrival detection. And for the artificial mixed signals, as we get much more signals to train the model, we get much better results. So you can see that using the synthesized signal is almost the same as using the real signal for direction of arrival, and even in some case even better. It seems that the error is better. So that was all I was going to present. So thank you very much for listening.
Thank you very much, Leandro, for your talk. Do we have any questions? Yes. Could you please, either you come here or we have to repeat your question. Okay.
I have a very basic question. I was very impressed with the results you showed on the denoising part.
Uh-huh.
And the basic question is, I don't understand what the neural network part is doing. So could you elaborate a bit more on that? And then the follow-up on that is whether this could be done in an adaptive fashion. So changing the weights of the neural net or something like that.
So this work we are referring to.
Yes, yes.
So one option you have when using a denoising autoencoder is that you could use the raw signal. So the raw signal this will be the noisy signal, and you train it to clean the signal. What we did is to use a coder. This is based on MFCC coefficients to codify signals. It's like an LPCD, encoder-decoder. So you can code the signal and decode with very good quality by using only the MFCC energy and F0 parameters. So in this case, instead of using the raw signal, we try to denoise the parameters. So that was the approach. We use the MCC parameters extracted by the coder, noisy ones and clean ones, and train the network to predict the clean ones from the noisy ones.
And was that done with different type of noises or just one type of
Yes,
noise?
in this work we used for each type of noise we train one different.
Okay.
Right? So we
It's
use
not a general-
white. No, it's not general. We use white noise, train one specific network for white noise, pink noise, another network. So,
Okay, I get it. And what about the second part of my question, where you have noise that could be very variable in time?
well,
Can you
we
make
didn't
it
test
adaptive?
that, but I assume that if you have several models, maybe you can switch models frame by frame. So this is frame by frame. So you extract one frame information, and suppose you can detect the kind of noise and switch the model or something like that.
Okay. And the last question I have is on the first part, on the blind source separation.
Yes.
I was wondering if you've used your methods for other problems like EEG, source separation, and source localization.
No.
If you've seen anything like
No, because in EEG, usually you don't need a convolutive approach because the distance from sources to sensors is small. So the instant model for independent component analysis fits quite well to that data. So usually they use standard independent component analysis, and they use it to do the noise of EEG and things like that.
that?
So
EMG, perhaps? EMG, electromyography?
maybe you can try. Yes, there are longer distances. For example, if you do a stimulus and measure distance, it may be interesting to try.
Cool. Thank you.
Thank you.
Thanks. Any other question? Yes, can you please step in?
I wonder, I have two questions first. I wonder why you, in the denoising application with the LS.
Here? No.
No, the other one. Here. Why you prefer to use a encoder-decoder network and not a normal network, a normal deep network for this application? Is there anything special about this encoder-decoder network for this?
In that time, the best model for sequences in that time was LSTM. So as we are dealing with a sequence of parameters, we thought that maybe it was better to try to use that kind of architecture. Then they came the gated recurrent units that are better than LSTM, and now we have attention mode that are better than LSTM. So we can try several alternatives. So, but at that time we thought that it was the ideal network, but we didn't try another approach. So it's something can be done.
And the second question is about, you talk about this beta divergence or beta norm here.
Yes.
There is any rule to choose this beta parameter for the application, or you just
Yes,
have to try?
we didn't get a general rule for all things, but we explored it and we get this kind of result for speech.
Okay.
So maybe it's not always exactly the same optimum for each signal, but in general, we can say that you need a larger beta in the first stage and a smaller beta in the second stage.
But it will depend on the application.
Probably in the application. And
I wonder about this. Is there any value of beta that, let's say, enhance sparsity, something like that? Because you talk about this beta.
In general, yes. What the main difference is in the, you can see it here, it's in the importance each kind of divergence puts in the amplitude. So if you consider the Frobenius norm, as it measures square difference, it will put more emphasis in large coefficients. So it inherits or it captures better the low frequency content, because in speech you have more energy in low frequency content. And then Itakura cycle divergence is like invariant to amplitude. So it can get good dictionary for the whole range. And this involves a smaller beta. So when beta approaches 0, you approach Itakura cycle. So we hypothesize that the mixture of beta we obtain is related to this phenomenon.
But there is any value of beta that will engage sparsity?
In general, sparsity is not introduced through the distortion, but through this additional term. So okay, if you put a norm 1 restraint over U, you get sparsity of U.
But
you can enforce it by specific terms on the regularization terms.
Thank you.
Any other questions? Yes. Can you please step in for the microphone?
My question was about investigation.
Yes. And this
I was
one.
wondering, because when you obtain non-negative matrices, you are using the spectrogram rather than the short-time creature solve. You are using the, the expectations to get positive matrices.
Yes.
So then you apply your NMF on your correlative model. But then in the end, the question is how you reconstruct the initial signal. Because then you have somehow.
I didn't say that.
The spectrum representation, but then how do you switch back to?
Yes, there are two approaches for that. You can either start with this. This is the clean spectrogram you produce, and you use the noisy phase and reconstruct. This is the first, but it's not the best approach. Yeah, okay. We use an alternative one. We use the estimation of speech and to do a Wiener filter and apply it to the noisy signal. Noisy spectrogram filtered with the Wiener filter obtained, time frequency Wiener filter obtained from the models of speech and noise. And that improves the results.
Okay,
so you can see the details in the paper, but basically you can try or mix both.
Because here you are measuring the discrepancy between the original signal and the.
Yes.
So not
in the
you're not measuring the spectrogram.
No. Once you get the spectrogram, you
okay,
can
so
go
was that what
by
you mentioned
inverse
in the
filter.
presentation?
Yes.
That was my first question, actually. Any other questions? Okay. Gabriel?
Questions about the second example that you gave us about the enhancement of voice using NMF, non-negative magnification.
This one? No.
This one. When you
Yes.
switch between this, I don't know, simple evolutionary model to the next one that improves the representation of the,
This one.
this one, yes. When you work with the second case, the much complex model, how do you guarantee that, or how do you assure that the information in the dictionary, the informations, every matrix follows the source filter theory or the phonation process in order to obtain a representative explanation of the signal using this kind of analysis method?
Yeah, we don't know. The one problem is a very good question because one problem with non-negative matrix factorization is that it is not unique. You can get several matrix product to synthesize the same matrix. So how you choose the one that is more proper for modeling speech. And we found that this can be done through the restriction. You can put restrictions. I didn't explain this in detail, but for example, this is a Lagrangian of H, so you try to force smoothness in H. And this produces a special H that better model speech, for example. But there is no guarantee, of course. You need to explore.
And another question is, what's the play of initialization methods in order to obtain good or not that good results?
Yes, in negative matrix factorization tend to be quite sensitive to initialization, so it's a good question also. But we found that for this application, it was not so critical. So we can use any initialization and get good results. Some of the matrix, I don't remember which one is initialized as ones, diagonal, so there is no problem there. But for the others, we have seen that it is not so critical in this application. Also, I didn't explain anything about the updating equation. This is a process, a complicated process where you fix one and update for the others and iterate it that way. But it is proven that it's guaranteed to converge. So there is a lot of room for improvement here. But
the last one, when you apply it, let's say in a real scenario, when you analyze the signal and try to decompose the signal based on the learned model, the dictionary and the relation model. How quick is the analysis method? No.
Yeah, it is not so quick. It can take some seconds.
Okay.
But it can be improved with more computing power.
It's faster than learning on the model.
Yeah.
Great. Thank you very much.
Thank you.
Any other question? No? Well, I actually have two, but the first question I had is quite similar to the one Sylvan's asked. How do you reconstruct from this spectrogram? You said you use the first choice would be to use the noisy phase. I mean,
Yeah.
But the second one, I didn't quite understood. You have like inner filter there.
Instead of synthesize clean speech from the spectrogram, the clean spectrogram we estimate, you can use the clean estimation as an estimate, and you can reconstruct also noise. And do an estimation of a Wiener filter, a time frequency Wiener filter, to enhance the noisy signal, spectrogram. So you, no, not spectrum, short time Fourier transform. Yes. So you get the short time Fourier transform of the original noisy signal, yes, and filter with the filter obtained, okay, from the estimation of the clean source spectrum. Okay. You understand? And you try to learn the filter. Yes, yes. The idea is that you get a better estimation of what the clean source is, okay, and you use it in a Wiener filter to enhance the noisy spectrum. Okay. So one problem we have is that there are some, this is not perfect, and there are some gaps. And so if you reconstruct directly from this, it doesn't sound that good. Let's put it that way. So if you use the Wiener filter approach, it gets a relative similar quality result, but it is more natural to use. Let's say.
Yeah, and just a final short question, because just out of curiosity, in your last application, the virtual source synthesis, yeah, I just want to know how many sources. It's just one source that you're recording?
Yes, yes.
One source.
This was a kind of preliminary study. We didn't know anyone in the world that was doing this, so please don't steal our idea. So we wanted to see if this is possible. We didn't know. So we tried a very simplified model, one source, 2 microphones, and tried a couple of rooms.
But the second one from only one.
Yes, yes. Also, we explored a little if we could predict independent of the room location. So we tried also to mix signals from the 2 different positions of speech. So, but that didn't give so good results, especially because of the number of sources of speech sentence we have. We tried that with the real speech data set, and it was too small for that learning. Okay. So there is a lot of work to do in that area.
Thank you very much. I don't know if there is any other question. I don't know, question from the virtual audience we do not have. No? No? So we thank Leandro again. We will be resuming at 2 p.m. for the second talk of the second day of the workshop. A las 2 de la tarde, entonces, arranca la segunda charla del segundo día. Gracias.